So there's no directions here, but what I'd like you to do is to just go through the 5 steps. Write the hypotheses, identify the level of significance, then gather the evidence, and that usually means to calculate a test statistic and a p-value. And this step is usually going to be done by the calculator. So there is a calculator function for each of the 3 tests in this section. The 2 prop z test is what we did in section 11.1. We went back to the t-test and we did a t-test on a single data set, that is the differences between 2 lists of data, dependent samples. And then the 2 sample t-test was what we did in section, the calculator function we used in 11.3. All right, and based on the p-value, you can make the decision, and then you need to interpret that decision, the conclusion. All right, so that's where we'll start. And here's the first problem, just to kind of go through these with you. A researcher wants to know whether the acidity of rain, so this is the pH, near Houston is significantly different than near Chicago. And big cities typically have lots of manufacturing going on and lots of pollution, and the pollution goes up into the clouds, and then that changes the nature of the rain. I did see a picture from India because of the social distancing and sheltering at home that they're doing in India. Now from one of the main cities in India, you can now see the Himalayas, and you've never been able to see the Himalayas from this city because of the pollution, but kind of the same idea. Okay, so he randomly selects 12 rain dates in Texas. Here's Texas, this is Houston. If you count them up, 2, 4, 6, 8, 10, 12. So N1 is equal to 12. And then a measurement was taken from Illinois, Chicago. And if you count these up, you'll see that there are 14. So the sample sizes do not need to be the same. And because they give us the raw data and not the summary statistics, we're going to enter in one of these sets of data in L1 and the other one in L2, and then go and calculate the mean and standard deviation from each of the 2 sets. And here you have the alpha, 0.05, and then the claim is down here. Does the evidence suggest that there is a difference? If they ask, if there is a difference in the pH, then turn that around to a claim and say that there is a difference in the pH levels. All right, so which claim would that be? Where would we put that claim, the null hypothesis or the alternative? So start out by writing the hypotheses and then do the rest of the test. The next one, number 2, treatment for osteoporosis. And in this particular case, they've identified from one sample here, from this one population, they took a random sample of 1,374 postmenopausal women. So women after they reach a certain age and they have menopause, then after that they're postmenopausal. And so they're just after a certain period in their life. Now what they typically do after they do the random sample of the individuals for a test like this, they'll split them into 2 groups. And they call this this is the experimental group. And then this would be the control group. Control group would be the group that actually doesn't take the drug. So in the experimental group, they gave 5 milligrams of this drug called Actonel. And the other group was given a pill that looks just like this one, but it was like a sugar pill or something like that. And we call that a placebo. And this is usually a double blind, these studies are double blind, which means that the person administering the medicine or the pill doesn't know if they're given the person involved in the study, the patient, they don't know if they're giving them the drug or giving them the placebo. And then the person who receives the drug, they don't know if they're getting the actual drug or if they're getting the placebo. So it's called double blind. And then they tracked them for, after they gave them this drug for a period of time, they tracked them over a year and they recorded those that had broken bones. And so of the 696 women who actually took the drug in the experimental group, 27 of them experienced a fracture during the course of the year. And over here, the second group was the placebo group. They try to break them up into halves, and they almost got there. And it could have been that, you know, some more dropped out of the placebo group than in the experimental group. And they found that 49 experienced a fracture. So the question is the drug effective in reducing the number of fractures? And one of the things we should always calculate here, since we want to know if the drug made a difference, and we're testing a claim about the relationship between the two population proportions, those that take the drug versus those that don't, it's always good to look at the sample proportions. So I'm just going to go ahead and calculate this quickly so you can see them and so we can compare. 27 with broken bones out of the 696 who took the drug, and that's 0.03, I'll call it 9. And then the other group, approximately, these are the ones that just took the sugar pill. They didn't really take a drug, so this would be what we call the control group. And as you can see, there's quite a huge difference. 3.9% of those who took the drug who didn't break a bone, who broke a bone, versus only 7.2%, almost double of those that didn't take the drug ended up with a broken bone. So because of this doubling here, we probably do have a statistically significant result. It does appear that, well, I'll ask the question, does it appear that this drug is working? And I'll let you consider that. But always do these summary statistics just to give you a sense. You've got alpha there. This one has a second part to it where you are asked to calculate the 95% confidence interval. But again, for this one, start off with the hypotheses and go through the 5 steps. And the third problem, researchers had a car travel at 10 miles an hour, collide into the rear bumper of an SUV. And then they went and fixed the cars and they recorded the amount of the damage in dollars. And then the data are below. So the Kia Forte, which is this car here, and the Hyundai Tucson, which is this SUV, they were involved in a crash. And you can see that the damage to the SUV was much more than the damage to the car. Whereas in this next one, the Jeep Patriot 1338 and the Dodge Caliber 25, it looks like the car had a lot more damage than the SUV. So for this test, we put the one vehicle repair costs in L1, and then we put the car repair costs in L2, and then we calculate the differences. And you can do L2 minus L1 or L1 minus L2, whatever your preference. And so for each one of these, we calculate the difference. And if I do L2 minus L1, you get negative 581. All right, so we're going to put these L3 values in there. And I showed you how to do that earlier with the calculator to crunch all those differences at the same time. And so at alpha equals 0.10, level of significance there, do the data suggest that the repair cost for the car is higher? start off again by writing the hypotheses and then carry out the 5 steps. This sheet that you see here, I'll leave it on the .cam so you can see it. It's a summary of the 3 tests from chapter 11. Section 11.1 is on comparing, testing a claim about 2 population proportions with independent samples. And this is categorical data. So this would be related to that problem that you just saw. Well, what do they keep track of? Well, the X's represent the number of patients that experience bone fracture, break a bone. So they're just counting them off. 27 broke a bone. It wasn't a numerical value. They're just counting them up. So definitely categorical variable. Where 11.2 and 11.3 involve numerical data, and the way we analyze numerical data is with means. The way we analyze qualitative data is with proportions. So, just going down here, this column describes what the other columns mean. Maybe I should. All right, the null hypothesis in each case. It turns out for chapter 11, the null hypothesis is always the same for these 3 tests. The alternative hypothesis, other than having selecting not equal to, less than, or greater than in each case, those are the same as well. The test statistic, there's always a formula. Luckily, we have a nice calculator test function that'll calculate these test statistics for us. In fact, the first output from any one of these tests will be, usually it's the alternative hypothesis, but then the first statistic that is reported is the test statistic, one of these. You'll notice that there's a pattern here, that for proportions, we use the Z distribution. There is a Z test statistic. The calculator function has a Z in it. The confidence interval formula has a Z in it. And we use the critical value, Z of alpha over 2. And we use the normal because Z is the normal distribution. So everything related to proportion uses a Z distribution and a Z calculator function. Whereas if you look at these 2 here with the means, every time we analyze means, we're going to be using a T distribution. You'll see a T in the test statistic. You'll see a T in the calculator test function, and also with the confidence interval. And the critical values will be, instead of inverse norm, inverse T. Again, there's your T. I'm just kind of gonna go through the overview of these. I'm not going to spend much detail unless you see something that, when you were working out the problem, that you had a question about something, and I can go through it at that point. All of these worked out solutions will appear in the lecture notes if you want to refer to them later on. This first problem is from 10.3, and the null hypothesis is always the same, that mu1 is equal to mu2. In this case, does the evidence suggest that there is a difference in the acidity or the pH of the rain in Chicago and Houston? And so we turn that around to say there is a difference. And if there is a difference between the mean pH levels, acidity levels, then the 2 population means will not be equal. So we're going to turn that claim into not equal. It's not specifying if it's not equal, whether it's greater than or less than. So we're just going to use the not equal to. Be sure you define the variables. Since these are population means, you should start off with the word mean. The mean rain acidity, or pH, in Texas, and the mean rain acidity or pH in Chicago. When you look at the summary statistics, this is what you should find. And so one way that we can maybe estimate if there's a difference is to look at the sample means. The sample means in Texas was 4.77, and the sample mean in Illinois was 4.509. So there wasn't a very big difference, 0.2 it looks like, or 0.25 or something close to that. a very, very small difference. So this might suggest that there's not a big difference in the pH levels, but we need to run the test. So level of significance given to us to be 0.05. And then we run the calculator function, 2-sample t-test. Now, for this one, we're going to select the data entry because we put our Texas data in L1 and we put our Chicago data in L2. That's what we have up here. So you should have these 12 numbers in L1 and these 14 numbers in L2. Frequency of those data values, each one, and this number down here, or this row down here, in our alternative hypothesis, we see not equal to 0. And since we don't know the variances, can't assume them to be equal, we're always going to say pooled equals no. So here's the input of the 2-sample t-test, and then here's the output. The test statistic, 2.276. When we get to be 2 or more standard deviations away from 0, the mean, then we're thinking that this is an unusual sample that does not necessarily reflect the null hypothesis. Small p-value, when we compare the p-value to the alpha value that was given to us, that number is less than 0.05. Our p-value is less than our alpha value, p less than alpha, so the decision when that happens is always to reject the null hypothesis. And then we write the conclusion. And since we rejected the null hypothesis, that the 2 population means were the same, we're showing support for the alternative hypothesis, which is also the claim. So when we write this up, we want to say there's evidence to support the claim. And then we want to say what this is. And so here's one way to write it. There's evidence to support the claim. And then just go on and state what the claim is. That there is a difference in the pH or the acidity of the rain in Chicago and Houston. So the test only tells us that there's a difference. You really need to look at the data to see what the difference is, and then you can report it after that. The acidity in Houston appears to be higher than the acidity of the rain in Chicago. And we make that claim because you can see that the sample mean in Texas is larger than the sample mean in Chicago. All right. For your reference later on, this problem didn't ask you to do so, but if you wanted to calculate a confidence interval to estimate the difference in the 2 means, if alpha is 0.05, then the confidence level would be 0.95. And the calculator function that you use is very similar to the calculator function that you use for the hypothesis test. The only difference is that instead of test, we have int. And then here's the interval. But what we notice about that is that both are positive. So when we're estimating mu1 minus mu2, this interval says that that difference is positive, which means mu1 is greater than mu2. So this is another reason why you can say that the average acidity in the first group, which was Texas, Houston, Texas, is higher than the second group. And we're not going to do the classical approach, but if we did, this is what it would look like. We're not going to do the classical approach for this test. Turns out that the degrees of freedom is this decimal number here. So, but if we did do it, you could see that the test statistic falls in the reject region. So again, the decision could be to reject. So you see all 3 approaches here: the p-value approach, the confidence interval approach, and the classical approach, all leading to the same decision to support the alternative hypothesis. Okay, the next one was our test. We know that there's a lot of tests going out there on testing drugs to combat the coronavirus. And the president is touting one combination of a drug, a malaria drug, in combination with an antibiotic. And that seems to have some success for some coronavirus patients, but these tests have to go through extensive clinical trials, and that combination for coronavirus, since coronavirus is new, has never been tested. In fact, you know, those who take that combination, 10% of them, if they have, you know, heart disease or some other underlying condition, it could kill them. And so we shouldn't be recommending such combinations of drugs, particularly to those folks who might have those underlying conditions. But apparently it's doing well for some. One of the things I want to point out about this is that we have these very low percentages here. And when that happens, you really should check to make sure that the sample size is large enough so that you can run this test and have a normal sampling distribution. And what's required is that you have NPQ for both of the two groups must be larger than 10. So I just checked them here, and to make sure that they were both larger than 10, they are. So therefore, we're just going to run the test as we normally would. Now, you might be confused by this less than sign here. Does the sample evidence suggest that the drug is effective? Now, those that took the drug, that was the first group. And so this is the population proportion of this first group is P1, and the other group is P2. And if the drug is effective, then P1 would actually be less than P2, because we're talking about broken bones here. And if a smaller percentage of those taking the drug had broken bones in the next year than those who didn't take the drug, then here's an example of the drug being effective, even though this percentage is lower than this percentage, because we're talking about the percentage that break a bone, and breaking a bone is not a good thing. So lower percentage means the drug is effective. And that's why we have P1 less than P2. It's a one-tailed left test, and that's also the claim. And here we define the proportions, proportion of women that take the drug that break a bone within a year. And then P2 would be the proportion of women that take the placebo that break a bone within a year. For this one, we have two proportions. So we're going to run the two proportion Z-test. You just enter in the X and the N, X2, N2, and then the alternative hypothesis has the less than P2 in it. You do that, you get the test statistic and the p-value. And here's the pooled proportion. Sometimes this is always calculated in the output, but it basically just takes the two X values here, adds them together, and divides by the sum of the two N values. It's called a pooled proportion, and it's used in the calculation of the test statistic if you do it by hand. Okay, so P is 0.003 and alpha is 0.01, and P is less than alpha. So we're going to reject the null hypothesis in favor of the claim. And the claim is that the drug was effective. So we want to say that. In layman's terms, this is how you would say that. There's evidence to support the claim, because we rejected the null hypothesis in favor of the claim, that the drug Actonel reduces broken bones in postmenopausal women. This one did ask for a confidence interval, 95% confidence interval. I'm not sure why it asked for 95 when our alpha was 0.01. So we would think, to be consistent, we would want to do a 99% confidence interval here. But even with a 95% confidence interval, P would be less than alpha. But what you should see about this confidence interval here, and when you type this into the calculator function, the first four numbers are exactly the same. The only other thing that you have to specify is the confidence level. And notice when you do calculate this confidence interval to estimate the difference between the two proportions, you see that the entire confidence interval is negative. So what we would be saying is that this thing we're estimating is negative. P1 minus P2 is less than 0 or negative, which means P1 is less than P2. And so P1 was the group taking the drug. It was less than P2. And that supports the alternative hypothesis. And I also did the classical approach, even though it didn't ask for it. This is a one-tailed left test. So we have all the area to the left. Here's the critical value that you get with the inverse norm function. And the left area is 0.01. And that would give you this number. And our test statistic, negative 2.714, is right there on that scale. It falls in the reject region. So again, the decision is confirmed using the classical approach. All right, I understand I may be going through these quickly, but if you need to see them, you can go download the lecture notes. In this next one, I gave you the setup earlier. We're going to put the SUV damage in L1, the car damage in L2, and then we're going to calculate all these differences. If you look at the average of the differences, and you should really report these numbers all the time, that the average difference in repair cost between the SUV and the car is about $1,672.71. I rounded these to 2 decimal places just because they're money they're money values. 7 pairs, so n is equal to 7. All right, so here's the scenario. Take one sample and we do 7 crashes between these cars and we go and get them repaired, find out what the repair costs on each of these are. Our null hypothesis in this test is always the same, that the mean of the differences is 0. So that 0 value that appears in the null and alternative hypothesis, that's what we call our mu0, that we would then enter into the t-test. Be sure to define the variable. This is the population mean of the differences in repair costs between a car and an SUV after a collision going 10 miles an hour. We're going to do a t-test on the differences. Now all the differences are in L3. So I select the data option here. There's our mu0 value, L3, frequency 1. And then the greater than corresponds to the sign in the alternative hypothesis there. When you calculate, you'll get the test statistic and the p-value. Here's the p-value. Here's the alpha value. P is less than alpha, so reject the null hypothesis. And if we reject the null hypothesis, then we would conclude that there's evidence to support the claim that on average, car repair costs will be greater than SUV repair costs after a collision. Now, there's another way to set up this test. If you subtracted L1 minus L2, then all of the signs of these differences would be the opposite of what they are. And if you took L1 minus L2 and got all of these signs, that's fine. You can do that. But the mean of the differences would then be a negative 1672, just the opposite of all those values. And if you do that, then you would have to change the sign over here because the claim is that the repair cost of the car is higher. And positive numbers like this one indicate, oops, positive differences like this one, the difference will be positive if the car damage number is larger than the SUV damage number. But if you subtract in the other way, then this is going to be a negative, and a negative would mean that the car damage is greater. So the way you subtract has to be consistent with how you set up your alternative hypothesis. All right, and then here's the classical approach. This is a right-tailed test because of the greater than sign. So we put all the alpha over here, and you see what the critical value is and how to calculate it. 10% there, so 90% to the left, and then 6 because the sample size is 7 and the degrees of freedom is always going to be 1 less than that. So there's the critical value. And then our test statistic, 1.927, falls in the reject region. So again, this confirms the decision that we're going to reject the null hypothesis. And it makes sense. SUVs are much bigger than cars. And so if the two smash together and the car's front end is going into the SUV's back end, then we would expect the car to be damaged to a much larger degree than the bigger SUV in most cases. Now, the reason I want you to put this down here on average, because if you say there is evidence to support the claim that car repair costs will be greater than SUV costs, it's not really the case, because here you can see that, in fact, the SUV costs were larger. So you don't want to make a claim that the car is always, the car repair cost is always greater than, because in some cases, like in this crash and in this crash down here, the SUV costs were actually larger. So you want to be clear down here that you're talking on average, not every single crash. And if you leave out the on average, then one might interpret that every single crash. So be careful the language that you use.